This week's lecture is about models that are basically linear models, but with a few twists. So let's start by recapping what we know about linear models. Linear models fit a hyperplane by taking a weighted sum of the input features. For regression problems, the hyperplane traverses the space of the features plus the labels, and we want the points in that space to be on or close to the hyperplane. Losses for regression problems attempt to capture this closeness. For binary classification, the hyperplane divides the feature space into two disjoint half spaces and separates the samples into those two spaces, associating a positive or negative label with each one. For these problems, we would like the samples to be well separated by the hyperplane. A classification loss function will typically attempt to capture the correctness of the sample occupancies of the two half spaces. Data that can be perfectly split by such a hyperplane is known as linearly separable. For multi-class problems, we have to fit multiple hyperplanes and then in some way adjudicate between them. This can be done either by pairwise comparisons or by some more collective approach like our softmax classification. A convenient interpretation of the outputs of a linear model that is being used for classification is as a score. This attempts to estimate the strength of our conviction that a sample belongs to a particular class. The scores are then passed through some kind of nonlinear decision function that actually does the class assignment. A common choice for this is just a zero threshold. Other kinds of nonlinearities might also be applied to the linear model outputs in order to impose some kind of structure or constraints on the score. For example, the sigmoid or softmax functions that we applied in order to ensure that probabilities add up to 1. As we saw last week, in the context of AdaBoost, the degree of correctness of a prediction can be quantified by its margin. If we use a labeling scheme of -1 and +1 for our negative and positive labels, then this margin can be quantified as the label multiplied by the score output. In this case, the margin magnitude is the strength of the prediction, and the margin sign indicates its correctness. So a positive margin means that you've got the right answer. A negative margin means that you've got the classification wrong. We've also seen that it's possible to apply transformations to the data before it goes into the linear model. This is in general known as basis expansion, and any arbitrary set of fixed functions can be applied. These functions form a basis for a different space that the linear model will be fitted in. The linear model is still fitting a hyperplane, it's just to this transformed space, not to the original feature space. The hyperplane in the transformed space may represent an arbitrarily complex decision boundary when it's translated back into the original feature space. But an issue with basis expansion is that choosing the new basis functions can be problematic unless you have some specific domain knowledge about the problem that guides you towards particular choices. It can also be expensive to compute the transformed vectors, especially if they are of very high dimension.